Good afternoon, everyone. Again, thank you for showing up tonight, our first meetup for the year. And like Sujit said, we're going to be talking about a topic called Think Cloud, Develop Locally. I'm going to share a little bit about myself before we get going. Like Sujit said, it's Mike Blakeney. I've been building and designing solutions for customers for the last 9 years. I started out as an independent contractor, eventually made my way over to Terazo, where I am now. I work there as a lead architect. My primary focus is designing solutions for our customers, along with supporting and enabling our teams and delivering some really good platforms. So we're going to explore some strategies and tactics on how you can analyze your software development work streams to help identify and mitigate some of the unique challenges in building cloud native applications. So we're talking about cloud native applications. So it's kind of baseline as to what we mean. So one definition we can look at is from the Cloud Native Foundation, and they describe cloud native applications as technologies that empower organizations to build and run scalable applications in modern dynamic environments such as private, public, and hybrid clouds. Containers, service meshes, microservices, immutable infrastructure, declarative APIs exemplify this approach. These techniques enable loosely coupled systems that are resilient, manageable, and observable. Combined with robust automation, they allow engineers to make high impact changes frequently, predictably, and with minimal toll. Another definition, this comes off of the Microsoft Azure website. Cloud native applications are built from the ground up and are optimized for cloud scale and performance. They're based on microservice architectures and use managed services and take advantage of continuous delivery to achieve reliability and faster time to market. So, we can kind of summarize some of the buzzwords that we see in there. When we talk about cloud native, we're talking about applications that are built with the intention to run into the cloud and take advantages of all of the goodness that comes from building applications in the cloud. Additionally, we see other attributes such as they're loosely coupled, resilient, manageable, we can observe them, and the big business sell is that we can enable high impact changes more frequently. That allows our businesses to be able to react and respond to rapid market changes. One thing I want to point out is there is a difference between building applications for the cloud and moving existing applications to the cloud. So when we talk about building applications to the cloud, they have unique challenges that we need to address. One of them is scaling horizontally. Cloud native applications are typically distributed in nature. So this creates challenges to how we're going to set up access and alerting, monitoring, logging, deployment. Cloud applications are often one part of an overarching workflow. And so you may have data points scattered across several different data stores in your architectures. Usually cloud native applications are going to live on some third-party provider, such as AWS, Google Cloud, Microsoft Azure. And this just means your team is going to be interacting with the nuances of these individual providers and the services that they offer. And then a lot of times, cloud native applications are deployed within containers, which means a container management platform needs to be added into the equation and all the required support for the application. And a container management service is something like a Kubernetes or leveraging Docker Swarm to help you coordinate your containers. And then on the same type of coordination, you may be coordinating this across multiple teams to deploy your application, and then also leveraging the full capabilities of the cloud, like we've mentioned before, in terms of scalability, security, cost management. So how do we address these challenges and all the other ones with our development teams and life cycles, when we usually build things on our individual laptops and then we go to the cloud? So the one thing that I'd like to communicate in this conversation, the one thing that you can that I'd want you to take home with you is how you work is just as important as the work you do. Everything else that we look at is going to be anchored on that one idea, and that the idea that how you do something is just as important as that thing that you're doing. So how you're writing your code, how you're deploying, how you are orchestrating your teams together, that is just as important as the work that they do. So with all that as an introduction, we can begin exploring how we can analyze the way that we work. We can apply some principles from lean process analysis as a tool for building out strategies that will optimize our development workflows and workspaces. And with the primary objective of this analysis as minimizing the amount of waste that's yielded as a result of our daily work. So the first step is to identify your value stream. What we mean by that is, as an engineering team, that value stream is everything that it takes, all the steps it takes for your code to go from your text editor, from Notepad or your IDE into production in front of a customer. So here's an example. You can see that we start by checking out some code, setting up a development environment, doing some testing, committing, etc. This is a very simple workflow, but you can probably begin imagining what this might look like in your organization and how complex this can become when you begin adding additional steps that are quite common, like architectural reviews, compliance reviews, security reviews. Different individuals need to sign off. This is your virtual assembly line, which means the things that you're doing, the material, your code is flowing through this stream. What can that look like? So it's important to understand what exactly flows through your work stream and how that impacts the quality of your software. So there's a book called Project to Product, where Dr. Mick Kirsten describes 4 different artifacts that can flow through your work stream. He talks about features, defects, risks, and debt. We can also think about how we can put controls around these things, put checks around features, defects, risk, and debt, and we allow them through the stream. These are important ROI conversations that are shared with your stakeholders, product managers, et cetera. So if you kind of look at these categories, pretty much all the stuff that we ship, whether it's intentional or unintentional, will fall under one of these 4 categories. And as technical teams, we need to have a good level of understanding as to how these artifacts flow and how they impact both our teams and the quality of the work that eventually gets put in front of customers. It's going to zoom into a little bit of waste, because we said we're going to look at how we can minimize waste. So we have an idea of what flows through, but what are the different, how can we analyze waste and categorize some waste? So there was a research done by a consulting group called Pivotal, and they published it back in May of 2017, and they identify 9 types of waste that they were able to look at in their customer projects. So they had all their customers, and they did surveys and tracked the projects, and they were able to categorize the types of waste into these categories. And so there were things like one category like extraneous cognitive load. These are things like complex or large stories, or diverse local development environments. Things that might take a little bit more brain power to compute than what should really be necessary, right? I kind of think of this as, if it takes a double take to understand it, then maybe it's too much of a cognitive load for you to pick up. Psychological distress. These are like low team morale, maybe interpersonal or team conflict. That's waste. We spend time arguing and bickering, or not able to work together. That produces waste in a team and impacts delivery. Waiting. This is stuff like waiting for access provisioning, dependency on other teams, new resource creation, even slow continuous integration and delivery processes. You have things like knowledge loss, and this is one that that caught me a little bit by surprise, because this categorizes things like team churn, knowledge silos, low priority on documentation. That one person that knows how the system works, they leave, and now nobody knows how that thing works, right? That's going to produce waste, because now we got to figure it out. Unnecessarily complex solutions. So we have lots of dependencies on external services, or we have very tight coupling with those services, or we may have a tool set that just doesn't integrate well together. And then there's the classic rework, right? This is technical debt. Maybe the stories are rejected by a product owner. The team has no clear definition of done, so they're having to go back and redo things, and just, old school defects. Now, you may notice that some of these categories of waste, they have some overlap with things that actually flow through our stream. And this is particularly important to address because further into the further any of this waste gets into our flow, the more costly and time consuming it can become to address them. This is where you may have heard about the idea of shift things left. We're talking about identifying this type of waste, these types of things in our workflow, and shifting them to the left. In other words, giving the developer, empowering the developer more and more to address these things early on in the process, so that we don't wait until it's in front of a customer, or we don't wait until it's time for a compliance review in order to address the issue. So going back to our flow, another area that we need to keep in mind is each individual step, there's a transition, there's a handoff. So those are also opportunities to where we can have waste. So when we're analyzing this workflow, we're not only looking at the individual steps, the stages, but we're also asking the question, all right, when I go from checkout to setting up dependencies, what does that handoff look like? Or when I go from running the app to testing the app, what does that handoff look like? Is there even a handoff there? Can we combine those workstations? So what we're going to do is we're going to look at some tactics now that we kind of have an overarching strategy, i.e. we want to reduce the waste. We have an idea of what that waste looks like. We know what goes through our value streams. What are some tactical things that we can do, things that we can take to the bank with us and cash in on in our development teams? So I'm going to come back to this. How you work is just as important as the work you do. So one strategy that we can take to implement this concept using lean principles is to encapsulate best practices into reusable project patterns. So reusable project pattern, they're basically solutions that can be easily shared and duplicated across your team and organization. They can be in the form of example projects, starter projects, reusable configurations, maybe reusable pipelines, templates. The important thing to identify here is that it's an artifact and it's a pattern. It encapsulates a best practice, and it's shared across the team and ideally outside of the team. So here's a possible roadmap that might look like for a project that you might be working on. All right. Step one, day one, first tactic of reducing waste is get your deployment pipelines up as soon as possible. Ideally, this is the first thing that gets built out. Your pipeline is what's going to move the code from station to station and ultimately to customers in your value stream. I mean, think about that, right? Like these are the 18-wheelers that take the product off the assembly line and bring them to the stores, right? They're going to bring them to the customer's front door. These pipelines automate those steps so that they're done exactly the same way every single time with as minimal human interaction as possible. You don't have to have a lot of functionality built out in your application to get one of these built up, right? Suppose you're building an API, for example. You can build something that has just a single hello world type endpoint, right? And then think about how you can put that into your app to push that out into a pipeline, right? So I have a minimal deployable application. I build my pipeline around that. And now I push that out. I can test the endpoint, validate that it's working. And then all my subsequent changes will actually be features, right, that are going to be used by end users. So the important thing here is to think about what is the minimal amount of work you need to do to lay out that first pipeline and get some code pushed into it and out into your cloud environment. Here's the other advantage, is that your development team begins to have a conversation with your operations or whoever owns those pipelines sooner rather than later. A lot of times it's not left to the delivery team or the engineering team to put those pipelines together. Oftentimes it's another team. And I can't tell you how many times I've worked with the team. We've built out a feature. We're ready to go. We've got, the world's best thing ever. It's going to revolutionize the world. And the whole thing comes to a grinding halt because we did not initiate the conversation with our colleagues earlier. It's no one's fault, right? It really is easy for us as an engineering team just to get tunnel vision on make the feature work, right? And then build really cool software. But we forget to engage the operations team. We forget to engage the compliance team or security team early on. Start those conversations early. Even with your QA teams, start those conversations early. Try to bring them along with you on that journey so that when it comes time to deploy, you have everything ticked off, you have everything ready to go, everybody's in alignment, and we go to production. The next hop on our roadmap is to localize quality. This is where we really begin to look at shifting quality to the left. What I mean is that we want to allow engineers to discover and fix quality related issues sooner rather than later. We've already touched on this a bit. Remember that defects is one of the categories of waste that can flow through our value streams. So catching the defects before they get too far down the stream will save both time, money, and stress. So how do we do this? Well, one of the things we can utilize are tools like static analysis and linting directly into our IDEs. You can use Git hooks and other tools to integrate quality analysis at the point in time where code is committed. And additionally, we can take these tools and put them into that pipeline and configure alerting, which is made very clear to engineers and is also accessible to your engineers. Other considerations is enforcing unit testing and integration testing, all were appropriate. So all of these things help engineers get feedback faster and address defects. Here's some specific examples for you. So there's a I'd say pretty popular tool called SonarCube out there. A lot of organizations leverage this to scan their code for quality related issues. Additionally they provide an open source tool called SonarLint. And what SonarLint does is it runs directly on your machine. And at the time of coding, it's more or less running some of the SonarCube quality analysis for you. So this means where your team might be dependent on a SonarCube instance that gets ran during a pipeline run, your team is now able to pull that left to them, and they're able to run these analysis in their IDE. So in this particular slide here, you see an example where SonarLint is catching a more complex type of a code smell. Here's another example of it catching a code smell as well. So after we have a basic pipeline in place and we're beginning to push those quality checks like linting, type checking, doing your unit tests onto the engineers, and those are integrated into their IDEs and integrated into our pipelines, we can look at how we can begin decoupling our applications from outside dependencies. So specifically, we look at what APIs we may be dependent on. So for example, we are working locally, right? Think cloud, work locally. So it's quite possible that there will be services deployed out into cloud environments where our application needs to work off of. So how do we decouple so that when we're working, when our local development isn't dependent upon making a call out to some cloud application? So we can look at these, okay, what are we going to need? These are candidates for running those APIs locally. So some of the things to consider when deciding to run these dependencies locally, you want to ask questions like, does the service have its own dependencies? Does the service need its own data storage and data? And can it even be run in a container, right? So you're trying to get this other service to run on your machine, and it might have its own dependencies, right? And you just end up going down this rabbit trail of, I need all these dependencies all running at the same time. A lot of times it's simpler just to mock the service APIs. This is particularly useful when you have an API client like a web app front end that needs to be built in parallel with the back end. Taking an API first approach and mocking these endpoints can enable you to continue front end development while the actual functionality of the backend is being developed, and the backend and front end feature sets are aligned based off of the API specs. So the first tool is to use OpenAPI to spec out and define your API. The OpenAPI spec is the next iteration on what was called Swagger. The OpenAPI spec supports definitions for not only your endpoints, but also return types, statuses, responses, authorization. And there are numerous tools that leverage OpenAPI spec to create interactive API documentation. You can do client code generation, backend code generation. There's just a lot of tools that have around that has make a good ecosystem. For example, the Swagger UI tool can be used to quickly generate an interactive documentation page for your API. And the OpenAPI spec becomes the contract for your client and backend to agree on. And this is an example of one. They're typically written out in YAML files and basically sets out all of your endpoints and the requests and responses, what those look like. So the next tool that can help with your dependencies is an open source tool called Prism. So Prism takes your OpenAPI spec and the examples you define to launch a mock server for you. So when you write out your OpenAPI spec, you're able to give it example data, example responses, and example requests. And so Prism takes that information inside of your YAML and automatically creates a mock API. So imagine that, like you have your API spec set up, you have your examples in there, and then immediately with a local instance of Prism running, you can have a mock API for your backend service. Now, what I think is really neat about Prism is it takes that up to another level. So when you run Prism in what's called proxy mode, it does two things. First, when a request comes in, it's going to try and forward that request or proxy that request to your service application. If your service application, the application you're building out, returns a response and it sends it back to the client. If the application returns a 501, then Prism will default to your API spec examples. So this lets you have more of an iterative local development approach where your a backend might have some of its feature sets ready and built out, but not all of it. And Prism can sit there in front and be able to make that intelligent decision as to when to use the backend and when to use the mock data. So we called this containerize your dependencies. So one tool we can be really helpful for orchestrating multiple dependencies is Docker Compose. Docker Compose takes a YAML definition of the services you want to run and launches them as a single stack. Here you see an example that shows you how you can use Docker Compose to spin up Prism in mock mode. By committing the OpenAPI spec and this YAML file to your code repository, a team member simply installs Docker, Docker Compose, and they run Docker Compose up, and they're able to quickly get everything they need for that project up and going. They have their mock API and any other services that are dependent going. So in this example here, you see we're grabbing the Prism image. We're going to forward port 4010. We're going to mount the folder where the OpenAPI spec is. We're going to mount that into the container, and then we're going to run the mock command and make the Prism available on the local host of the container. Now, one thing to keep in mind with Docker Compose is that as you add more service dependencies in here, this file can get pretty big and unmanageable. So it's really best suited to really only mock out the application, one application and its dependencies. It's not always ideal to have your entire microservice architecture inside of one Docker Compose file. And in fact, at some point, and this is really a function of your team and the application you're building, you will probably come on to a point of diminishing returns, in which case your development style will need to pivot to leveraging other types of tools other than Docker Compose, particularly when it comes to trying to figure out how to best integration test something. So since we're talking about containerizing things, we want to free our databases. Another dependency that you want to consider containerizing is your data stores. In the same way that we can use containers to run our APIs or services we may need, we can set up Docker Compose files to also run these databases locally. especially if you're using popular open source databases like MySQL and Postgres. So with this, your team can then leverage tools for handling schema migrations and seeders and efficiently make changes and run consistent versions of the database schema on their independent projects or on their independent local development environments. So here's an example of what you might do for a Postgres database in your Docker Compose file. And note that we are also running the service for Prism, and we've introduced another application called Addminer. Addminer is something that I personally I like using it. I would never put this in production, but it's great for local development. It's basically a single PHP app, and one file, which I don't recommend either, but Addminer just makes it kind of cute. But it's one file, simple, and it's a very easy just UI client for pretty much most of your SQL related databases. And in a containerized environment like this, you can see it's really easy to get up and going. You just say, hey, go use the Addminer and open port 9000, and it's ready to go. It's going to give you a nice user interface so you can access that container or access the database. And again, it gives you a great starting point for your new engineers, right? You have new engineer that comes on the team with a single command. They're able to get their database going. They have a convenient web UI available for them, and any of the services that the application needs are already ready to mock out. So you can see we've added it here. We're using Postgres 9.6. We're opening up the Postgres ports. We've got Addminer running, and again, we've got the example pet store service running here. So the next thing we need to look at, we've moved our databases, we've got them in containers. Now we need to maintain a consistent schema across those databases. And one way we can use that is by leveraging schema migration tools. Now, these are tools that enable teams to make incremental changes to databases. One of the primary advantages to using schema migration tools is that it guarantees that changes are made to the database in exactly the same way every single time. Additionally, suppose you were to check out a SQL file that has a SQL for standing up your databases, right? Like you could very easily just, export a SQL file, commit it to Git, you're ready to go, right? But what happens when that changes? You are going to you have a V2 version of the database schema, and that V2 version doesn't necessarily describe how the database changed from V1 to V2. In other words, I might export my database schema for V1, then export my database schema for V2. But how do I make that change? How do I alter my database? The SQL file is from Big Bang, right? From point of 0 point of time. So the schema migrations allow you to do that. Using a series of migrations that declare things like create the table, update a column, it allows a team to not only incrementally apply changes, but also track what changes have been applied to the database. So that when you check out code by simply running a migration tool on your database, you will catch up to the latest state of the schema. Now, one of the other interesting things are tools like Liquibase, and that makes it easier. It makes it easier to manage it through YAML files. So what you see here is an example. This is a change log for Liquibase. The other thing that these migration tools will do is they typically keep a table of all the changes that have happened, all the migrations. And if someone were to come in and commit a change to, say, this 01, right, after it has been ran on that database, Liquibase will kick back an error saying, well, somebody has changed a change log or a migration that has already been run. That makes the state inconsistent and unreliable because now I don't know what state the database actually is in. So we need to go back and undo that change. So it gives you the ability to make those changes and know what changes have been made and prevent those types of alterations in previous changes. You almost think of this like your migrations is almost like a commit log of what's going on in your databases. The advantage here in relationship to the cloud is that now my team doesn't all have to connect to the same database and potentially run into schema collisions or data collisions where we're all trying to work on the same data set, or maybe I'm adding a feature that requires a table to get dropped or a table to get added or a column to get changed, and that's going to impact the rest of the team. I can do it in complete isolation, roll back, roll forward, do whatever I need without impacting the other team. All right, now when we're building cloud native applications on cloud providers, you probably choose to use some of their SaaS offerings or some of their managed offerings. And these are typically in the form of queues, blobs, other storage blobs, other things like that. And you still need to interact with these APIs, but you also want to be able to develop without having to depend on these services. In other words, if I'm building out a queuing system, I don't want to have to depend on an SQS queue for all of my engineers. It would be really nice to be able to swap out the backing service for something that you can run locally and then swap in the cloud provider service when you're ready to integrate it. This is really similar to what you might see in a lot of ORMs, where it's really simple to swap out a Postgres from MySQL database without the actual business of your business logic and your code changing. Right? It's strictly a configuration. You just tell the runtime environment to use MySQL instead of Postgres. Well, in this, we want something like this, but for all of these different services. So here's where we would start looking at something like maybe a strategy pattern. It's going to encapsulate several different algorithms that an application can easily swap out. So instead of coding the algorithm or coding the interaction directly into our application, the application receives instructions on which one to actually run. Here's an example. So here we see that we have the ability to run RabbitMQ locally, and then SQS when we're ready to integrate with the cloud provider. The strategy context encapsulates which strategy to actually execute, while the application itself is completely agnostic to the chosen strategy and only interacts with the strategy interface. The context can easily be set through something like an environment variable. And once these libraries and strategies are built, developers can focus on the business logic of the specific use case and not worry about the details of interacting with a cloud provider's specific implementation. So in the above example, a developer can set an environment variable to point to the application to use RabbitMQ when they're running it locally. And then that enables them to focus all on the business logic and not have to worry about the nuances of um, the individual queuing provider. And then when they want to test against a dev environment, they could possibly switch their local one to dev, or there might be some type of dev sandbox that they can push their code to, and that would allow them to interact with what's actually there. The queuing that's more closely like what's going to be in production. So like we saw in the previous tactics, Docker Compose can also be used to spin up RabbitMQ. So I can add RabbitMQ to my Docker Compose, and now my application is able to manage its database locally, any type of queuing service locally, and then also the API dependencies. This kind of brings us to our next tactic, and that's adopting standard architectural models and patterns. And why would we want to do this? Well, for one, it will teach best practices to new engineers coming onto the project. Second, it's going to reinforce best practices with the rest of the team. And finally, it produces examples for how to solve those common problems. All of this boils down to helping engineers quickly figure out how to solution for a problem and give them the opportunity to focus the majority of their creative energy on solving new and more interesting problems rather than how do I connect to the queue. One example of a framework or set of architectural rules that can help developers is the 12-factor app. So the 12-factor app was introduced as a framework or way of thinking about cloud native apps by Heroku back in 2007. The principles apply today just as much as they did. In fact, it's even more significant given the shift to containerized deployment of applications. So for example, 12-factor apps should use environment variables to configure per environment settings. 12-factor apps should scale horizontally with a single process, right? Logs should be streamed from standard out, and there should only be one application to a code base. All of these remain very important concepts to apply when building cloud native applications. And applying best practices for containers can also be a huge help. Here's an example. Um, Applications should be deployed as one or more stateless processes with persistent data stored on a backing system. Stateless architectures are paramount to building scalable, reliable microservices. Achieving stateless applications means that nothing is directly shared across the processes. In other words, even if the application scales horizontally, it should not be concerned with the state that is stored in the memory of another application. Applications should prefer to share state either in databases or in some type of caching tool like Redis. This is particularly tricky when you work with real-time applications or need a persistent TCP connection. So care should be taken when you're looking into technologies like WebSockets or even some of your newer gRPC connections. Another one is fast startup and shutdown are advocated for a more robust and resilient system. This is the disposability principle. So disposability is summarized succinctly in the familiar microservices saying of we want cattle, not pets. Applications will fail and is more efficient to treat running app processes as disposable things than things to spend the money, effort, and emotional energy it takes to maintain a single server that can never go down. What's significant with this factor is that it is dependent on the following several of the previous factors, like having your environment and having environment configurations, using backing services, and utilizing concurrency. Because we use Docker containers, the following best practices regarding their construction and best practices regarding the construction, we're able to quickly create and destroy and restart applications with little to no impact on what's going on around it. Another example of architectural models is standardizing how some of your applications or projects might be laid out. And this just helps ensure separation of concerns and good code organization. Additionally, it makes moving across projects that much less involved because there's a common way of doing things, right? Like if you have a common way of organizing your Node applications with your Python and your .NET Core applications, if you have a polyglot type scenario, then if you go to one project structure to another and they're all laid out and organized in a similar fashion using similar concepts in layering and communication, then it makes it that much more easier for a new engineer to come on or even move across teams and projects. So here in the above example, we have like an API, an application, domain infrastructure layers, and you can kind of see how we've distributed some of the communication there to interact with the database. And basically, maybe it's showing like a basic CRUD application or something like that. So with all this in mind, you can get to a point to where you can begin to extract out reusable components, patterns, and ways of work. These become the building blocks for your library of reusable patterns and ultimately starter applications that are completely scaffolded out with best practices and optimizations from the lessons learned by others on your team. All right. Are there any questions? We'll check the time here.
Yeah, I don't think we have any questions yet. So please feel free to jump in and ask your questions. If not, okay, there's a question there in chat.
Let's see. So Mike, yeah. So explain stateful versus stateless application again. Yeah, okay. So a good way of thinking about stateful application versus stateless is there data if I'm building a system that's horizontally scaled, right? So I have my service and I have it running instance A, B, and C, right? Um, each one should be able to run independently of each other. In other words, if instance B dies, then A and C shouldn't even care. And what that allows you to do is scale these out as much as you need, or scale them down as much as you need without impacting your performance. A lot of times you're going to see this when maybe you're working with socket connections, because in a socket connection, you're making a direct TCP link between, say, a front-end application and your back-end application. And so if my front-end app is connected directly to, say, service B, and service B goes down, well, then my front-end app is impacted, right? A and C cannot pick up that load, right? However, if I take that TCP connection and I use something like Redis to persist the fact that connection's there across the other apps, then I'm able to push that state into something like Redis and not have to worry about if any of my other applications die out. Another way of thinking about it is if I'm doing some type of counter, maybe it's a counting visits to a website, and I'm load balancing the count across different across those A, B, and C, then the fact that the request went to A shouldn't impact the fact that it went to B. In other words, if I hit A, it should still go to 1, right? If I hit B, it should still go to 2. If I hit C, it should still go to 3. That's a stateless application. Stateful would be if it hits A, I'm at 1. If it hits B, I'm at 1. If it's C, I'm at 1, because each individual application is maintaining its own state on that session. I hope that helps.
While we wait for questions, one thing I was wondering about was, does it, these principles are more generic, but are there things that we should concern about for different clouds? So let's say AWS versus GCP versus Azure. Are there things that make a difference that we need to worry about?
And as in how you approach building an application, or?
Right. I know the principles you have laid out here are more high level than that, but I was just wondering from a practical perspective, are there any things where it can become a little tricky because the cloud products are not exactly the same, right? Like they all have variations.
Yeah, and I think that's just it, right? Like there's the nuances in each one, right? And I couldn't really tell you you better watch out for that without deep diving into one specific service offering, right? So here's a example of there's AWS SQS, right? You've got to build your services. You've got to build services that are omnipotent. Is that right? Idempotent, right?
Idempotent, yeah.
Omnipotent is I'm really potent, right? Idempotent is basically, it means that when I put something in the queue, or when I take something off the queue, I should always be able to make the request. I should always be able to process that request the exact same way and get the exact same outcome. In other words, the fact that I get that event twice, because Amazon guarantees at least once delivery on these, on particular queuing. That if I get the same task twice, I should still get the same result. So my application should be intelligent enough. And that does happen. When you get into, and it doesn't have to take a lot, I've seen it in the thousands, right, of tasks, you're going to get the same requests. What are the costs to make a common abstraction to different APIs, to different technologies? Yeah, it's a good question, because when you're building out these abstractions, there is definitely a development cost to it. And one of the ways that I would think about it is as an investment. In other words, if I build an abstraction for being able to swap between RabbitMQ and SQS, then that's going to become a reusable shareable library for my team or my organization in such a way that the teams, one, no longer have to worry about a lot of the nuances with those services. They can focus more on the business logic, and then other two, they can bring it into their projects and they have what they need to get started. So I think it would be an investment up front with the payback in the form of reusability, consistency, faster delivery.
Yeah, there's a comment about the Dapper framework, DAPR, and I hadn't heard about it. I just looked it up. Looks interesting there.
Yeah, that's the nice thing about doing this on Zoom, right? We can all get on Google at the same time.
Yeah. So yeah. So yeah, stepping back to the multi-cloud thing, I think one thing that, and it actually does tie into this question about abstraction, and I think we need to be a little bit cognizant about not getting carried away, right? Like, so like if we're trying to build that perfect abstraction that will like solve world hunger, I mean, we should be careful about that. Like, especially in situations where like we are a consulting firm and we are spending the client's money. We don't want to spend like months trying to create that abstraction framework. It is more like, how can it help us develop locally? So we already know the target that we want to, like AWS or Azure, and then let's just abstract between that and our local environment and not try to build this framework that's all in, trying to solve everything. So.
Well, there's also tools, there's tools that can be used. AWS specifically has one. I'm trying to find it. LocalStack. LocalStack is an open source tool that their free version mocks most of the most common services you're going to use for AWS, and it mocks them all locally for you. So you really could run a mock SQS service or a mock S3 service on your local box. And we've used that tool in the past before on projects, and it's been a good one to use.
Okay. Any other questions or thoughts, comments? We have a little bit of time left. So thank you again, Mike.
Thank you for having me.
Yeah, and thanks for kicking off this 2021 season and setting us in the right mindset for developing for the cloud. So once again, thank you to everyone for showing up today, especially the new RDU meetup.